Good morning, everyone, and welcome to the third day of the FY22 CINR webinars. We're going to have a question answer session after each Workscope today, but we just wanted to remind everyone after this webinar, please submit your questions to neup@inl.gov, and they will be forwarded to the correct people for answers. This morning, we're going to start our presentation with CT3 and Dirk Carnes-Gallimore. Dirk, go ahead and take it away. Thank you.
Good morning, everyone. My name is Dirk Carnes-Gallimore. I'm the lead here at DOE headquarters for the Advanced Materials and Manufacturing Technologies program. This is a new program that I'll give you a little bit of background here shortly. We have 3 areas under CT3, and I'll go over briefly what those areas are, and then I'll pause to give our technical leads a little bit of time to add some additional information to those areas as we go through the presentation. So here's our standard boilerplate slide on how to ask questions during the webinar. We use it through our software. Our questions that don't get answered will be a lot of time. We'll answer those as best we can through the NAUP.gov site. Specific questions on individual eligibility workscope details should be addressed offline. We'll do our best we can to answer all the questions as possible and as we go forward. So a little bit of background. In the FY21 appropriations, Congress did provide funding for a new program to strengthen the pipeline of new materials that can make the current fleet as well as new advanced reactors more resilient and economically competitive. The U.S. Department of Energy's Office of Reactor Fleet and Advanced Reactor Deployment is working to establish a new program, Advanced Materials and Manufacturing Technologies Program. This is the program that the CT3 section that we're talking about will be under going forward. Our plan is to achieve this new program through integration and coordination of existing programs and continued collaboration with the best expertise in government and our partners, such as the university programs here. Our challenge is to align our materials and design, modeling, and simulation manufacturing and demonstration R&D efforts towards a focused, goal-driven process and products whose end uses are then adapted to market conditions. As you'll see, we go through, we've got several activities beginning with in the program and flowing towards a certain near-term and longer-term goals that we'll discuss briefly. Kind of some points that help define our program. The AMT is merging of 3 other existing programs: our Advanced Methods for Manufacturing, the Nuclear Materials Discovery and Qualification Initiative, and our Transformational Challenge Reactor Program. We're doing this for one, to make a more holistic approach within the materials program of the NE52 and as we move forward. The program is intended to address a life cycle approach for our materials. This includes the design of the materials, what are other existing materials and newer materials, manufacturing and creation of the process of these materials and the products, our validation, verification, and testing, understanding our performance requirements on the materials, and then certification, acceptance, and qualification. And finally, we also supply chain and sustainment. That way we have an approach that does consider from how we design a material, how it's made, and of course, what is the supply chain that's going to be required to deliver that to our market conditions and support our advanced reactor community for now and into the future. So the vision for the program, we have several programmatic goals. Of course, we've got to strengthen the pipeline of our new materials and establish that holistic vision that I spoke about earlier, understanding the supply chain needs and priorities, and our ability to deploy and maintain reactors and determine the priorities of various materials for the program itself. We also want to increase our collaboration among all of our stakeholders, and through that, drive this iterative process of development, implementation, and acceptance of these technologies to more rapidly to adapt to the changing environments and to more quickly get material solutions and design and production solutions into the market. How are we going to define success for the program? We want to define programmatic success not as, okay, the program itself is one goal, but sub-elements to that. So we want to deploy the deployment of domestic economically viable technology as well as the scientific and engineering expertise support its use. So we will judge the success of the program by how quickly or how we are actually deploying our technological solutions or options for industry. And we want to ensure that the solutions and options that support the current fleet and new advanced reactor technologies. And this is really kind of key to the program itself, is that we have an end use driven approach and also creativity as well, so that we can come up with solutions as new problems are identified within our industry. So what have we done? We've initiated several activities. The first, we've got data collection, and we requested information on materials and manufacturing infrastructure from industry. We've done a kind of we've started and completed some initial literature reviews. And the function of these was to ensure that we had an updated understanding of our current industry efforts, make sure that the future work proposed maximizes support across our stakeholders with limited or no duplication of activities, and provide data to help prioritize our research and investments. The other effort is looking at how materials and material systems are qualified in the advanced manufacturing area. We have an upcoming workshop that is on August 24th and 25th. This is an initial discussion that is probably going to continue into the future. And the purpose of this is to begin to develop an integrated approach to the advanced materials and manufacturing technologies qualification process for materials, components, and identifying the current challenges. Our goal here is that we want to understand how we qualify our materials and our material systems now with all of our new modeling and simulation activities and testing capabilities. What would the qualification look like, or what should qualification look like if we leverage all of those capabilities? And we have more information on the GAIN website. We've got several partners associated with it. We've got EPRI, NEI, and of course our GAIN folks. So as I was saying, we have three different areas under the CT3. All three of them are going to be supporting the idea of deploying these materials, and of course the qualification efforts that we are moving forward with. Our first area, our technical POC, is Isabella Van Ruin, and it's of course universities only. Up to 2 years and about $500,000 are awards. When we look at our new materials, the economic demand of new reactor technologies under diverse conditions, we want to expand the application envelope of our materials and product systems from current qualified materials portfolio and manufacturing processes. The idea is that we do have quite a few different material systems that are applicable during different conditions. We know that in some cases with our current materials that no single material can be a comprehensive solution. And so we need flexibility in our material systems for multiple reactor systems, and we want to do multi-material systems to address some of those near-term issues. So we have these possible solutions. We want to enhance our economic robustness of our designs. So multiple cladding and coating technologies for specific reactor systems, being it MSRs, gas reactors, liquid metal reactors. We want to minimize the mechanical transitions or welding between dissimilar metals. We do have, an example is off to our right, where we have our 316L pipe and our Inconel and our different our SA508 nozzle. And this is an example of a very complex weld that requires multiple material systems in order to accomplish the joining of these materials. And part of the multi-material systems goals is to look at how we do this and if there are different new approaches that we should be taking. And so we want to minimize the complexity of these weld systems and make sure we have the equivalent or better performance. And so the other element to this is looking at functionally graded materials as a consideration for these interface systems. So instead of a multi-part weld, you have one weldment that is graded material across the entire complex. And so we're seeking an integrated approach for pretty much an agnostic gradient material verification methodology in terms of interface and residual stress requirements. We want to include a gap analysis on earlier research and current standards, modeling and simulation activities, the use of digital twins, accelerated testing and characterization of proof of concepts. We want a detailed justification for the material and manufacturing process choices that would be used for the proof of concept. And we really do want an industry partner. The research is aiming towards the development of these advanced reactors and deployment in the future. So having these industrial partners is going to be a critical need going forward. Now that there's several other avenues and more information and I want to give at least Isabella a few minutes to add to this as well. Isabella?
Thank you, Dirk. Can you hear me well?
Yes.
Thank you. Yeah, the schematic below on the slide try to provide the researchers a possibility on how to attack this agnostic gradient methodology. And basically, we do not want to pinpoint you to a specific material, but we would like you to develop or produce samples from dissimilar metallic materials, but specifically then motivating why you are choosing those materials systems. And I can envisage here that it potentially depends on your industry partner or partnerships that you are including, but then also composite material and metallic ceramic materials. And the reason for this is to show really to us that this methodology that you propose is applicable to basically any material system. Yes, it is really motivational, but it depends on your specific justification. And for each material system in the dark blue, you can choose any two manufacturing methods that you, again, will justify why you choose those materials. And specifically then for each material system, each manufacturing system, you will describe the interface behavior and the minimizing or eliminating the residual stress and the measurements for this. So it seems complex, but we believe that with this, it will provide the wider community really with a verification methodology that will be very helpful for all of us going forward. And with that, Dirk, over to you.
Thank you, Isabella. The next area, CT 3.2, advanced creep mechanisms. Our technical POC is Alan Roach. It has the same, eligibility requirements and funding. And so the background for this one is the deployment of advanced reactor concepts requires materials that can withstand extreme environments, innovation in radiation, high temperature, and non-aqueous corrosion. Innovative materials design, manufacturing, and testing is required to accelerate the development and the qualification of these new materials. A new approach to the nuclear design cycle is desired, focusing on the transformational materials design, advanced additive manufacturing, and accelerated testing. When looking to develop novel approaches to assess time-dependent phenomena relevant to reactor licensing and operation on a reduced timeline, such as accelerated testing results. So what are we looking for this proposal? Modeling, simulation, and/or machine learning methodology for clarifying specifically creep mechanisms to overcome the traditional surface to bulk constraints, limiting our sample specimens to sizes and to interpret experimental data. Methods developed by the proposals, the characterization techniques should be ones that can be deployed in radiation environments such as hot cells. Alan, is there additional information you'd like to provide as well?
No, I think you covered it pretty well. We're really looking at focusing on creep for advanced reactors, and we want to use AM to make functional small-scale structures such as lattice structures and unique materials to minimize that creep mechanism, especially in the advanced reactor environments of enhanced radiation and higher temperature. Other than that, it's covered well. Thank you, Dirk.
Thank you, Alan. And then our final area is high throughput testing for advanced manufacturing materials. And our POC for this is Ben Betzler. And again, the same requirements as before. Additive manufacturing techniques yield large amounts of location-specific data in situ that are stored in digital threads for a given part or component. A corresponding manufacturing digital platform uses AI techniques to establish links between characteristics within these digital threads, and then the our post-manufacturing data sets. Generating test data for a variety of material properties is critical for developing and demonstrating a digital platform-informed approach to component certification. Advanced manufacturing benefits from a large amount of data that is generated as part of the manufacturing processes. As you see, we're looking at ways we can harness all that data and appropriately. So the proposal request, this focuses on the development and application of novel, high throughput thermophysical or mechanical property testing that can yield spatial data with at least 1 millimeter resolution for additive manufacturing builds. They should include a detailed description of the proposed measurement techniques and the method to store and track spatially resolved data. The trace of material and additive manufacturing process should be appropriately justified. Ben, is there anything else you would like to add?
That covers most of it, Dirk. Thank you. Just one point of focus is that it is important to specifically define the amount of data that this novel kind of method would yield. More data is very much desirable for the application of a digital platform in the way that we have envisioned it. It's not really necessary, but more data is always better. Thanks, Dirk.
And thank you, Ben. Those are the 3 areas for the AMMT program. They're all very much materials focused: analysis, testing, and designing and fabrication. With that, we will gladly answer any questions that are available.
Okay, thank you very much, everyone, for that presentation. Our first question, is the literature review mentioned in CT 3.1, is that available as a report?
So we can go back up to CT 3.1. I think what we're asking to be done is that you guys do literature research so that we know that you're not duplicating other practices or processes that have already been developed.
Correct.
Okay, great, thank you. Next question. You mentioned industry partnership is required. Does a DOE national lab qualify as an industry partner?
No. DOE labs are not considered as an industry partner. They are there as a use for anyone who is available. But when we speak about an industrial partner, we're thinking about the actual folks who are going to be deploying this technology on a commercial scale.
Okay, next question. These seem to be excellent projects tailored to long-term industry needs. However, the budget seems to be rather low regarding the goals. Do you anticipate alignment with other programs? And if you do, which ones?
I think that one of the things that we're asking to be done here, yes, these we're asking for creativity. We understand that the budget numbers here are low. We expect that what we develop here is going to be applicable to multiple reactor systems. Specifically, we'll probably be partnering with the NE51 activities and the ARC programs as well. Depending on the material systems, we would also be inclusive of those folks that are working in our fuels group as well.
Okay, thank you. For CT 3.3, are you envisioning an in situ characterization method during the AM process, or can this be ex situ?
Ben, would you like to take that one?
Yeah, sure. Thanks, Dirk. Yes, we would. It is written more in mind ex situ characterization processes, but in situ certainly, if you adequately define that in your application, that is something of interest. Please make sure to review the current state of the art regarding characterization of additive processes. when you formulate that approach.
Okay, another one for 3.3. Does additive manufacturing include processes such as advanced electroplating?
Yeah, so go ahead and look at the accepted definition for additive manufacturing, which includes a host of processes: directed energy deposition, sheet lamination, powder bed binder jetting, as well as laser powder bed fusion. Those are the main ones that we would kind of focus on. Yes, so please review that.
Okay, one more along that same line. Are advanced reactor conditions such as high T, non-aqueous corrosion of any specific interest in 3.3?
Yes.
Okay, we'll stay on 3.3 for a minute. Is there a preference for data collection during the build process versus collected post-build?
No preference. Again, make sure that you have traceable data from a spatial perspective. So once things are removed from any build plates or larger pieces, it needs to be spatially traceable to where it was during the build, and in general, because we're looking at those characteristics during the build.
Is it possible to get samples for 3.3 from the Department of Energy?
Hey, Julie, that's a question I'd like to take offline. I think that the team in internal land need to discuss that one and to see what's available first before we make that offer out to anyone.
Okay, that sounds good. We will get an answer for that, and we will post it with the Workscope Q&A so that the answer is available for everyone later. Okay, next one. Can you explain how the call this year for 3.3 is different from last year's call?
So last year's call was very specific on the TCR materials that were available. This one is much more broad. And so there was specific materials like 316L, 718, and silicon carbide that were available last year. Those are possible options, but it is a much more broad scope this year.
I'll add to that, Dirk, on the method to generate the data. It is also more broad as well. Last year, we were focused on those materials and near-term kind of methods to generate data for qualification of these parts. So it is significantly different in those two aspects, materials as well as methods.
For 3.3, are we required to collect the digital twin data?
I think that's one for you, Ben.
Thanks, Dirk. That's a little along the lines of what we need to answer on the previous question that Dirk kind of set aside for the time being. But I would say at this point, no, it is not expected that you collect a digital thread.
Okay, and one more for 3.3. Does the proposal need to include both mechanical and thermal physical properties, or can the proposal focus on only one of those?
They can focus on only on one.
Okay, let's switch back to 3.1. Is this call expected to investigate a specific component system considered in advanced reactor designs?
Dirk, would you like me to take it?
Yes, I would, Isabella.
Yeah, thank you. No, it is more to describe a procedure, a process of how you would approach gradient, functional gradient material to either minimize welds or to provide functionality to a specific part. And that's why the focus is in the description that you need to look at the your justification of why you use the different material types, and prove it that it is really agnostic, either for metallic ceramic or metallic, etc. So it is you need to prove it that it doesn't matter what your material is, it is the process, it is the methodology that you need to develop. Thank you.
Thanks, Isabella. Okay, for 3.1, are multi-materials for fusion reactor components of interest?
So this call is for our advanced fission reactor, so we're not necessarily interested in advanced fusion materials unless they can be applied to the advanced reactor community. But we're not interested in developing the materials for fusion.
Okay, another one for 3.1. What environment and conditions would you envision for the functional graded materials applied as environmental and thermal barriers?
Again, here we were not prescriptive to the research community to pinpoint you in one specific or two specific venues. It's all about your approach and how you justify that approach to make it so that it is agnostic. With other words, you can apply the methodology to a variety of systems, not necessarily you prove it by different material systems to show that you can use it either or. So therefore, if you want to go for high temperature, high corrosive in one go, that it is your for you to justify it properly, as Dirk said earlier as well, to prevent any duplication of previous work and research well publicized. Thank you.
Great, thank you. Okay, one more for 3.1, then we'll move on to 3.2. Is 3.1 focused more on modeling and simulation or on experimental analysis, or is it a combination of both?
I would think that it is a combination of both, although it needs to be validated by your experimental systems. Thank you.
Okay, I do see another one kind of along the same topic, but with a more specific question. Functionally graded material 3.1 is similar to some high throughput testing 3.3, such as combinatorial materials study that use graded compositions to rapidly test alloy systems. For a combination materials study on coatings, would you consider that appropriate more for 3.1 or for 3.3?
So 3.1 is really geared towards the testing itself. Yes, we're interested in data, but we're developing the concepts of high throughput testing in various different characteristics of the materials. And 3.1 is looking at the methodology of how do you verify and certify multi-material systems. So I understand how they are related, but the focus of them is slightly different.
Okay, let's move on to CT 3.2. Is it only interested in creep mechanism? How about other properties and phenomena?
A good question. Austin, I'm glad I got a question. I was feeling really left out there. So we picked creep because we know this is going to be a challenging problem with material design. And obviously, we're interested in creep corrosion, cracking, I mean, all of that will be of interest, but we thought we needed to focus since we're looking at a fairly small year in scope. So that's why we picked creep. Obviously, if you have a really good proposal that can work in 2 years and 500,000 and take on another physics phenomena, please do. But we decided to pick one to make it more focused.
How about ion irradiation? Is that of interest in 3.2 or 3.3?
For 3.2, yes, of course, we're always looking at ion irradiation. It gives us opportunities, if we can correlate back to a real neutron environment, to be able to do irradiations quicker, faster, and maybe control the physics a little more. Of course, we all know the challenge is tying it back to the real nuclear reactor environment. So yes, if there's a strong correlation to a reactor environment, ion irradiation is certainly encouraged. Ben?
Yes, as well, as long as it fits into this this narrative of generating data for a digital platform for 3.3.
Okay, back to 3.2. Would nanoindentation-based characterization techniques be considered?
Oh, absolutely. And we're also encouraging here, you know, if there's ways to integrate multiple tests together for accelerated measurements, that would also be included. And you know, we've been looking at nanoindentation too, because it has a possibility of being combined with other tests. So absolutely, yes.
Okay, next question. Thank you. For CT 3.2, is the creep behavior of nuclear fuels other than structural materials of interest for this topic?
Yes, that's a good catch. It should say fuels and structural materials. Now, granted, we are focusing on, you know, in this new area under Dirk, and I'm assuming Dirk will jump in and answer this too. We are probably looking at focusing on only a couple materials. So for example, like 316 stainless. However, developing the capabilities to design a fuel would also be of interest. So yes.
Thank you. Okay, a follow-up question for CT 3.3. Is there any published technical reports that could be recommended?
Yes, absolutely. TCR.ornl.gov has, in general, the most recent up-to-date information on what has been published regarding in situ data that we're taking, the concept of the digital platform for part certification, as well as the data that we have generated from additively manufactured components and the materials that we're looking at. So tcr.ornl.gov/publications has a whole list of those publications, kind of get you at least righted in that concept, as well as the data that we're generating and the methods that we've been using to generate that data.
Great, thank you. Would you be interested in the post-heat treatment process of 3D printed materials in one of these work scopes?
So I think when we look at this, almost all the work scopes, you know, post-heat treating gets us to the end product state, in which that is where we're going to be interested in all the data. So I think it's going to depend on how the proposal is structured and what they're asking to be done.
For 3.2, should the focus be only on additively manufactured materials?
So since we're combining this into this new AMMT, where the focus is advanced manufacturing, we are picking additive manufacturing techniques as the focus, so that allows a natural link between 3.1, 3.2, and 3.3. So I think the preference would be yes, but if there are unique advanced manufacturing, I think we'd be interested in that, but then we'd have to you know, I'm going to pass it to Dirk. Dirk, what do you think?
I mean, I think when we look at all the various ones, I think we're open to it, but we have to remember what the goals of each of these sections are, especially from the creep methodologies, which I understand can vary because our materials properties do vary and our structures vary between our different advanced manufacturing methods. So again, it's going to be depending on how well the proposal is written and the specific goals that are going to be accomplished that meet the scope that we've provided.
Thank you. Okay, next question.
My apologies for 3.1, if I can just add on, it is not only limited to additive manufacturing because you can produce a gradient material by a variety of technologies to support there. It depends on your justification and your approach that you take. Thank you.
Now we have just a few ideas people are asking about. First is selective laser sintering considered as a promising way for materials synthesis? And then in parentheses, there's porosity.
So I'm not sure that we're going to comment on any specific, additive or advanced manufacturing technologies within this forum. That really needs to be left to the proposal and the justification that's being made by the individuals.
Great, thank you. There is one more general question. Should only fusion or powder-based AM processes be considered, or can solid-state AM processes be included?
Yes, they can.
All right, everybody, that looks like that's all the questions that we have for this section. So thank you very much to our presenters. Just as a reminder, if questions come up after this presentation for these work scopes, you can always email the questions to neup@inl.gov. And we will resume at 11 a.m. Eastern Time for RC3 and the IRP NEAMS 1 work scopes. Thanks, everyone.